Okay, questions? Maybe give me a second, let me try.
I have one question.
Yes.
So let me open the slides first and then.
Okay.
So actually, I didn't understand one thing. So so there is this theorem one which is about a Berry-Esseen CLT, right?
Yes. May I ask you to also, like, do you have a video so that I can see you?
Oh, yes, sure. Yes.
Yes, I can see who's talking. Okay.
Sorry.
Oh yeah. Okay. Good. Good.
Okay.
Good to see. Okay. So what is it?
Yes. So there is this Berry-Esseen theorem, right? And
Yes.
after that, you gave an example that the bound in this theorem is tight, which is 1 over root n. And you gave
Yes.
this example of Sn equal to n over 2, which scales as roughly 1 over square root of n.
Yes.
But this, I don't see how this implies that the bound is tight, because Sn equal to n over 2 is just saying that Zn is equal to 0, right? That's how you define Zn. Zn is Sn minus n over 2 by something. So Zn is 0. So Zn you define in the previous slide, which is Sn minus n over 2 divided by square root of n over 4. So that its mean is 0 and variance is 1. In example 1 on page 6.
Right. So what this is saying is that Zn equal to 0, the probability of it is 1 over root n. Yes.
Yes, but the Berry-Esseen says there's probability of Zn bigger than or equal to t. It is not like
Yes.
for equal t. So I don't
That's
know.
what I'm. Right. That's what I said. You need to do a little bit of argument. So yes. So that's it's a little bit. So let me see if I can share my screen. Okay. See if I can show you this. Okay. So you see the screen, right?
Yes, I see your screen. Yeah.
Right. So what you can do is, from this, sort of argue that the probability that Zn, let's say Zn is in t, and t plus delta minus the probability that g is in t and t plus delta. This is also going to go bounded by root over. So maybe there's a constant here, but let's say there's a constant here. Could be 2 or something. But that's for some constant, this is going to hold. And then this also holds for any delta.
I see. So you take limit to be delta.
Yeah, you could take the limit and take t to be 0 and delta make it.
But in that limit, because then it depends on because that constant, right, that you wrote c of rho, so that also may have dependent on delta. So if you take delta to be 0, so that might also go to 0, right? I don't know. I mean, I don't know how that scales.
That doesn't go to 0, because when you do, so what you end up showing is that this is going to be, so this is going to be bigger than, so the other side, Berry-Esseen says this should be less than, the other side is going to be bounded by a constant over root n.
I see. So for all
no, for t is equal to 0 and delta is small enough. I can show this. Delta is small enough. Right? So Zn is not going to be, so pick any n, right? If you pick any n, then the probability that Zn is in 0 to delta, if delta is sufficiently small, is going to be the same as the probability that Zn is equal to 0.
Yeah.
Right? Yeah. And this can be made arbitrarily small by making this small. So this would be 1 over root n, and this would be like epsilon. So then you can get your result.
Yeah, so the key is here to show the lower bound that you just, or
Yes,
say the.
yes. So it can't be made much smaller than 1 millimeter. That's the idea.
I see. Okay. Thank you.
No problem. Okay, other questions? So this is like.
Okay.
Let's do this. Take this out. Put it here. Idea how to prove the lower one. And various things. Okay, that's this. Okay. Good. Other questions? Okay, so let's maybe keep going then. So you started talking about the how to. Oh, yes. Question? Did anyone say anything? Let me open the chat here so that's. Okay, so you can also send things in the chat. I'll try to monitor that. So what we end up doing was, it's actually too much. So let's try to take this out. Maybe this so there. So we started with this idea of Chernoff bound, and so we had the random variable zn, and we wanted to control the tail, so the probability that zn is greater than or equal to t. We did this interesting transformation. So you raise, so you multiply by lambda, which is positive, and you raise e to the power of lambda zn, and also the other side. So you can do that because the exponential function is increasing, as was pointed out, right? And so what we end up doing is we then apply the Markov inequality. So Markov inequality. And what we get is this bound, which is called the Chernoff bound. So you get exponential, like the expectation of e to the lambda is the n, which is the MGF, normal generating function of Zn, divided by this quantity. Okay, so in order for us to use this bound, we need to control the MGF, but you can see the sort of exponential nature of the bound is here. So this is like e to the negative 1 over e to the lambda t is e to the negative lambda t. So if the MGF is well behaved, then we can hope for an exponential bound that we like. So this led to the idea of defining class of random variables that are called Sub-Gaussian, and a random variable which is 0 is called Sub-Gaussian with parameter sigma if the MGF satisfies this inequality. Okay, and if a random variable is not 0, we consider the deviation x minus expectation of x. This would be 0 mean, and if this random variable satisfies 1, then we say that x is Sub-Gaussian. So a Gaussian random variable self-satisfies this, with parameter being the variance. But other variables also satisfy this, including bounded variables. So any bounded variable, almost surely bounded variable, here, for example, x is in A and B, then it's going to be Sub-Gaussian, and the Sub-Gaussian parameter can be estimated. So this is an estimate of the Sub-Gaussian parameter. So the Sub-Gaussian parameter is not unique. So for example, this holds with this, I can multiply by 2 as well. But this is a fairly sharp bound, as if from one of the homework problems hopefully shows. Okay, questions? This is just a reminder of. Okay, so then we sort of had this proposition that shows that if you have a sub-Gaussian random variable, then you have this nice tail bound. So let's say x is 0 mean. Then the probability that x is bigger than t is less than or equal to e to the negative t squared over 2 sigma squared for all t. Okay, let's maybe try to prove this first, and then I'm gonna come back and tell you more about it. Okay, how do we prove this? Can anyone tell me how to prove this? Proof. So let's say I start writing probability that x is bigger than or equal to t. Okay, then what? Let me help you. So I'm going to do the Chernoff trait. So e to the lambda x is bigger than or equal to e to the lambda t. Lambda is positive, and this is going to be bounded by e to the lambda x divided by e to the lambda t. This is the Markov inequality. What is the next step? Are you awake?
Use the property of the Sub-Gaussian.
So Sub-Gaussian thing.
Yes, yes, yes. So you just
Properties.
do this. So this replace or use this inequality basically. So e to the sigma squared lambda squared over 2. And then I can also put the denominator in here as lambda t. Okay. So that's by Sub-Gaussian. So what is the next step? So we have now a bound. It's a tail bound, but it doesn't look quite like what we want.
So, but you can minimize over lambda.
Yes, so that's the idea. So whenever you have a bound that is dependent or includes a parameter, then you want to find the tightest bound. So I want to find the tightest bound. So I minimize this side over lambda because this holds for any lambda. It's going to hold if I take the infimum over lambda. And how do I take the infimum? This is basically going to be just, I just have to minimize the exponent. So
Yeah.
minimize the function that maps lambda to sigma squared lambda squared over 2 minus lambda t. And
yeah, so lambda will be t by sigma square or something.
right, so you could do, this is like a quadratic function, and it's fairly easy to figure out. So you could just take the derivative, set it equal to 0 if you want, or if you're not happy with that, do something else. But this is going to be lambda t. Let's say t star is going to satisfy this. So this is going to be, right, so it would be minus t, let's say equal to 0.
And there won't be a 2 here because 2 and 2 will cancel out, right?
Yes, right, so you'd get sigma squared lambda. So t star is sigma squared lambda, and you plug back in, and so things simplify because the two terms are going to be the same, in fact. Like that one would be one half the other, so you get negative lambda squared sigma squared over 2 if you haven't done it in t squared.
And variable here is lambda.
Right.
So it should be star on the lambda. And
yes. So thank you. That would be t over sigma squared.
Yeah.
Right. So you're solving for. So that would be e to the negative, hopefully t squared sigma squared over 2.
Is it divided by?
Yeah, divided by sigma square.
Yes. Okay, you can see that I trouble writing the right thing. Okay, now it's correct. Right? Okay, so the rest is simple enough that you can figure out, and this is just the result that we want. Okay, let's compare this with this one, and we're done, right? So that's a simple application of Chernoff, and this holds for any t. As you can see, there's no constraint on t, and lambda is gone. So one thing that you have to be careful about is this assumption here, right? So taking the derivative set equal to 0, because it's a constraint optimization, you have to make sure that the result satisfies that constraint, which in this case satisfies it. So this is not going to hold for t. So the assumption is that t is bigger than or equal to 0, or let's say t0 doesn't make, t0 is fine, but let's say t is bigger than 0. You could put equal 0 is fine. So t bigger than or equal to 0 makes this lambda star valid. Otherwise, the function does not achieve the global minimum at the location where the derivative is 0. It's just going to be hitting the boundary. So you have to be careful. We'll see an example of that. Okay, so just make sure that you're minimizing and respecting this constraint. Questions? Okay, so that's the basic proof. The claim here is that I can do the same. So basically the same bound holds if I replace x with negative x. So I can just as easily write here probably that negative x is bigger than or equal to t is less than. Because negative x is also zero mean and is also sub-Gaussian and is also going to satisfy this. Okay. So expectation of e to the, if this holds, then expectation e to the negative. This is going to also hold. Right? For all lambda. Do you see why?
I mean, you can take lambda to be minus lambda, but right hand side will be the same.
Yes. So take this holds for any lambda. Replace lambda with negative lambda, and you get this inequality. Like the same holds for negative lambda instead of lambda, and that's the definition of sub-Gaussian for negative x.
I see.
Okay. So x is gonna have negative x is gonna have the same property. So if this holds for x, this is gonna hold for negative x. So I would have the same inequality here.
Okay.
So now, can I from this conclude something else? So from these, I would like to conclude the bound on, from these, I want to get probability that this is less than or equal. So yeah, so the value is bigger than or equal to 2. Yeah. What can I get?
2 times union.
Yes. Okay. So this is going to be the union bound. So this is going to be the probability. If you haven't seen it, you have to do it once at least. So this is x bigger than or equal to t, or x is less than or equal to, or we can write it this way: negative x bigger than or equal to t. And this is a union of 2 events, right? So this is probability that x bigger than t union negative x bigger than t. Union bound says that this is less than or equal to the probability of individual one, x bigger than t.
Events here are disjoint, so probably you will have equality. Because
really?
Because both of them can't be satisfied simultaneously.
They can be if
How?
X is equal to t, right? I'm not going to worry about that case, but yes, you might be right. So there is some intersection if X is equal to t. No?
I mean, whatever t you take, if you take
And
t
t
to
is
be
0. For example, let's say x is equal to t is equal to 0. And they both hold.
yeah, but that is a probability 0 event.
It's not necessarily probability 0.
No. Okay.
We don't know. Yes, generally, if I've written something like, yeah, so if you had like strictly bigger than this, right, then
Okay.
you would be. You're right, but you're not going to need it.
Okay.
You could write it in a way that, but this is safer.
Somebody
This
is
is
saying they are not just disjoint. Okay.
there are very like corner cases in which this way,
Okay.
but you don't need to worry about this. So this is, and then this is both of them bounded by that. So you get e to the, both of them are bounded by the same quantity. So you get 2 to the e to the negative t squared over. In the theorem, we can, someone said if the t is negative, they're not disjoint.
Yeah, but t is not negative.
Right. But could be 0. You can ignore the, so okay. Maybe you guys can say it yourself instead of me reading it. Daniel, do you want to give your comment? It would be better.
Yeah, so we can't actually ignore the case t equals 0 because then the exponential just becomes 1, and so it gives it like a trivial upper bound. And in that case, then we would actually be able to say that these two things are disjoint, and then we have like an equality.
Right. Yes. Okay. Right. You might be right. Yeah. So this might be tight, which is interesting. Yes. But I'm used to writing this because this is safe. But yes, if you really want to do it, you can probably in this case. But the thing is that eventually, at some point, you have inequality. So you're going to lose. It's not going to, at this point, it's inequality, right?
Yes.
And if you have equality there, you're not going to have equality in the next step. Okay. Okay, good. But this procedure that we did here, this is very common, and so you should be comfortable. So oftentimes people drive one of these bounds, and then the next follows, and then the deviation form, which is bounding this, follows. So this is common enough for people to just state one of these. Sometimes just mention that the two-sided version. This is a two-sided bound. This is a one-sided bound. The two-sided one follows from the one-sided, and you just have to make sure that you don't forget about the two. Yeah, so that's the statement here. And then what happens if expectation is non-zero? So you can just apply this result to x minus mu. This is zero mean, and by definition, Sub-Gaussian, it just means that x minus mu satisfies this. So all the things that we did holds for x minus mu, and you can see the result holds. So this result, this is the general form, right? So you don't need to drive it for general mu, you just do it for the zero mean case, and the general case follows. Okay, so now this is a concentration inequality. So example of a concentration inequality. It shows that the probability that x deviates from its mean in either side of the mean is exponentially as small as you move away from the mean. Questions? Okay. So you can see the Sub-Gaussianity has interesting properties. The next step is to do some sort of extensions or develop some calculus to work with these Sub-Gaussian variables. So the next proposition gives you an interesting result. Assume that xi's are independent. Zero means Sub-Gaussian parameters sigma I. Then the summation of them is again Sub-Gaussian with a parameter which can be written as the square root of the sum of squares of the other parameters. Okay, So the Sub-Gaussian parameter, so don't look at the proof here. So the Sub-Gaussian parameter behaves like a square. If you square it, behaves like the variance. It's not the variance, but it behaves like the variance. So for example, we know that so we know that variance of Sn is, what is the relation of the variance of Sn to the variance of the other?
Summation of the variances because they are independent.
Yes. Okay. So that's this, and so if you look at this as sigma squared is summation of the individual ones. So the Sub-Gaussian parameter has this same similar behavior. It acts like the standard deviation, but it's not the standard deviation in general. Okay. So what is the proof? I have the idea there.
The variance.
Someone wants to give the idea of the proof.
Yeah. So each so we can write down. We can upper bound this. We know by definition each of them is upper bounded by e to the lambda square sigma square over 2.
Right. So you write this down. Why this is what I wrote here is true?
Because of the independence of xi's.
Yes. So this is expectation of e to the lambda.
Summation.
Right. Just do it once maybe. So this would be expectation of the product, I from 1 to n e to the lambda xi.
Yes.
And then this would be expected product. This is the independence. And then what I have is, what do I have then?
So we can upper bound this thing by e to the lambda square sigma I square by 2.
Right. This is by Sub-Gaussianity.
Yes.
Actually, there's some I here. Each one is sigma squared I. So I get that.
By 2. So you can take the product inside. It will be summation. So e to the lambda square sigma square by 2.
Right. And then this thing is, by definition, sigma squared. Right. So this is going to be sigma squared. And so you get e to the lambda squared sigma squared over 2, which is showing that the result is, by definition, that this is e to the lambda squared sigma squared over 2. And you're done. That's the end of the proof. Okay, so this is very interesting because now I can apply, I know that Sn is Sub-Gaussian, I can apply this result to Sn. Sn is 0 means Sub-Gaussian parameter sigma squared. So I immediately get this interesting result. So assume that xi's are independent of 0 means Sub-Gaussian parameter sigma I. Sigma squared is the sum of the sigma I squared. Then this is the Sn. The probability that Sn is bigger than t is less than this. Everyone sees that? It's just a combination of this result with this result. So apply this with x equal to s sub n. And then this holds if you replace xi with negative xi. And so you would get the two-sided version as well. Right, so you could get probability that I from 1 to n, xi is bigger than t, is less than 2 to the x, negative 2 to sigma squared. Okay? Sounds good?
Yes. So t square.
So this is for 0 mean case. What if things are not 0 mean?
Same thing. I think you can do the same Yeah, so inside this it will be summation of xi minus expectation of xi,
right?
and it will go through.
So you would do something like this. So this is the result that you can show.
Yes.
Say negative t squared over 2 sigma squared. Okay, because Sn minus the expectation of Sn would be the summation of xi minus the expectation of xi. Each xi minus expectation of xi, call it a yi. Right, so this thing is going to be Sn minus expectation of Sn is like summation yi. I from 1 to n, where yi is the centered value. And so you apply the result to yi. And yi is our sub-Gaussian with parameter sigma I. And so you're done. Okay, so you have a very nice result with which you get with much less work than expected. Okay, you didn't do anything fancy with the sum. You just drive this for a simple case, and then did a little bit of. You can see that the main part is that the MGF is factorizes for sums of independent variables, and that's the basic building block that gives you this result. Okay, and then you can also do, let's say, consider the zero mean case. You can do some reparameterization. So you can look at the sigma, the average of the sigma I squared. This is like a average sub-Gaussian parameter squared. And then you can also look at the average of xi's instead of the sum. And so I can rewrite that, that result there like this. It's not difficult to do this. If I replace, what I would do is I would replace.
If you replace t with nt, it will.
Yes, so I replace
t with nt.
t with nt.
Yeah.
Right, so you would get nt here, n squared, t squared here. So I can do that because this holds for any t. And then divide both sides by n. So you get here, this is going to be the probability of x bar n bigger than t if you divide by n. And the other side, I can put one of these in there, so you get x negative t squared. There's an n here, and then 2 sigma squared over n. And this guy is going to be sigma bar squared. Okay.
Mm-hmm.
So that's usually what statisticians do. So you write things in terms of the average, and you can see the average is sharply concentrated. So I could also do, for example, the two-sided version of this. So you can put here this and then a 2 here. Right? That would be the deviation version. And so x bar n is sharply concentrated around 0. Shows that x bar n sharply concentrates around 0, because you can see the n here. So as I let n grow, as n grows, the bound goes down. So the bound goes down exponentially fast. Right, like e to the negative some constant times n. If you think of t and sigma bar as fixed. So it's reasonable to assume, let's say, that these xi's all have similar sigma I squared. Then the average would be of the same order. Let's say it's a constant. So this average would be a constant. And then t, you can take it to be a constant. Let's say 5. 5 times I don't know, 5 times sigma bar, for example. And then for sufficiently large n, then things would be the probability would be very small. Okay, so that's why it's called the concentration inequality, because it gives you high probability results. So for example, let's say I have, for example, let's say take t to be, I don't know, alpha times, let's say take it to be, let's say 2 times, or yeah, 2 times sigma bar. Then the probability would be less than or equal to 2e to the negative 2 n, right?
Yeah.
Yeah, and this is quite small. Let's say if n is equal to 10, this would be 2e to the negative 20, which is what? What is e to the negative 20? I have to do a little bit of calculation here. Would be 2 point, and then we have to multiply by 2. It's about 4 times 10 to the negative 9. It's very small. So with a sample size 10, if you go twice as far as is it correct? Might be correct. It doesn't work for the Gaussian though. So this is too small even for the Gaussian. Did I make any mistakes in there? Doesn't seem so. So you 10 to the negative 9 or 10 to the negative 8 is very small. So it says if you go to sub-Gaussian parameters of A, then you're not going to be there with very overwhelming probability. And for the Rademacher case, for example, these things are, let's say sigma bar would be sigma I equal 1. So if you have symmetric Bernoullis, let's say, then if you take t to be 2 times 1, the chance that you observe, so if you have a symmetric Bernoulli, then this is going to be a symmetric random walk. So in this case, what color should we use? So Sn will be symmetric random walk. So if our calculation is correct, it's saying that the chance that the symmetric random walk after 10 steps is within an interval of 2 and negative 2 is, sorry, 2 times n. So the probability that Sn is negative 2n and 2n is bigger than, the probability is bigger than, let's say, 10 to the negative 8. Okay, with the high probability, you're going to that.
Sn will always be within minus 2n and plus 2n, right?
Yes, that wasn't a good choice. Yeah, right. So you could do, this is not a good, yeah, you're right. Yeah, so you could do a better job here. So let's remove this. But you could do it with other, not 2, let's say. You could do it with smaller t. You could do like 0.1, right? Then you could say, yeah, so do it yourself, but Sn will be a symmetric random walk and you have a bound, right? Okay, good. Other questions?
I have one question. I mean, not on the math here, but just about like, why do we study sub-Gaussian random variable? I'm just asking. Apart from the mathematical beauty of that, but like, is that any like? I mean,
because of exactly
Gaussian
this
appears in the CLT, right? I mean, that is well motivated.
Yes.
But why do we study sub-Gaussian? Where does it appear, or is this like, where do we use these things?
So there are two answers. So one is because it's a useful class, because the class has a useful property. The other one is that I mentioned that all the bounded variables are Sub-Gaussian.
I see.
So anything that you know about bounded, let's say anything that you know about Sub-Gaussians, you have it for bounded variables. And
okay.
The idea is that they're called Sub-Gaussian because their tail bound looks like the tails of a Gaussian. So they go to, like the tails go to 0 fast, like e to the negative t squared. Whereas, for example, Cauchy tails are very slowly going to 0, right? Polynomially going to 0. So there are random variables whose tail behavior is as fast as a Gaussian. So these are Sub-Gaussians. And I'm going to talk about equivalent characterization. An equivalent characterization is that any random variable whose tail behaves like this, or in fact whose tails behave like this, is a Sub-Gaussian variable. Right, so you care about Gaussians because of different reasons.
Also satisfies this.
Yes.
The proposition 1.
Right. This is, do you remember? Right?
Yes.
Yeah.
So yeah, I'm still not clear. Is there a situation where you cannot use Gaussian, but you can use Sub-Gaussian? I mean, is there any place, like any?
Obviously, this is.
Anyone wants to answer that question? I heard something. You can answer the question if you want. Any bounded random variable. Yes, that's what I mentioned. So the thing is that it's not up to you sometimes to decide. Yes, if it was up to us, we would always work with Gaussian variables.
Okay.
But it's not always the case. So you could have like an experiment in which you have count. And then Gaussians are not good models for counts. Or you could have a 0, so positive random variable, let's say. You could have other situations where...
I see.
But this is one class.
Got it.
Right?
Got it.
Good.
Got it. Thank you.
Yes. Okay, good. Other questions? Okay, I don't know if this slide is readable at this point, but you got the idea. So that's the Sub-Gaussian bound. Any more questions? Okay, so let's move on then. So this is the thing that I wanted to mention. So there are equivalent characterizations of Sub-Gaussian. We defined it in terms of the MGF, but you can equivalently define it in terms of the tails or the moments or some other characteristics. And this is nicely done in the HDP book, High Dimensional Probability Proposition 2.5.2, which is roughly restated here. And I'm going to state the result, and the proof you can read in that book. And it's going to be good for you to go through the argument. So the idea is that a random variable x is going to be Sub-Gaussian if any of these equivalent forms or statements hold. So the first one is that the tails of x satisfy this type of decay, which is the decay of a Gaussian for some constant k1 for all p. This is one characterization. The other characterization is that the moments, so the pth moment of a random variable is defined like this, denoted like this. If the pth moment scales like root p for all p bigger than or equal to 1, and there could be another constant here. And this constant k2 is going to be related to the k1 by so-called universal constant. So for example, k1 could be less than or equal to twice k2. And then k2 would be less than or equal to, I don't know, some other constant times k1. So they're equivalent constant in terms of, they're equivalent in terms of, in the sense that there are inequalities between them with factors that are only numbers. They don't depend on anything else. So they're related up to universal constant. 1 implies 2, 2 implies 1 for constants that are in that relation with each other. And also they're both equivalent to this other statement, which we did not actually yet. I mean, so the MGF is bounded like this in a neighborhood of 0. And if you compare with what we have, so what we had before is this. So we stated the result for the case where the expectation is 0. So in the case the expectation is 0, they're all equivalent to this other term. So this is saying that this holds for all lambda. But the thing is that if you want to verify the argument, it's equivalent to this. So you don't need to prove that this holds for lambda, if for all lambda. If it holds for, oh sorry, this is not this is this statement about the x squared. So the MGF of x squared, not x. So if the MGF of x squared satisfies this inequality in a neighborhood of lambda, then your random variable is sub-Gaussian. And the weaker statement is, so weaker than 3. So under like, at least on the first look or the first reading. And you look at this, I shouldn't say this. So it looks like it's weaker. So, but 3 and 4 are actually equivalent. So this is saying that a random variable is sub-Gaussian if you look at the MGF of x squared and the MGF at any point, if there exists some point at which this is bounded. So if x squared has a bounded momentary function at some point, then the random variable is going to be sub-Gaussian. Okay, so these two are equivalent, from which you can deduce that if x squared has MGF.
What do you mean by bounded at some point? Because expectation is a number, right? So
the MGF is this function. T maps to this. The MGF lambda maps to expectation of e to the lambda x squared. That's the MGF as a function.
So you're saying for some lambda.
Lambda, yes.
Oh, okay, got it.
Right, bounded for some lambda. Yes.
So I was wondering, for the fourth equivalent condition, where does the 2 come from? Can we always rescale K4?
That's a good question. I believe so, yes. Why there's a 2 here? And can we get rid of this? You could definitely do it if you, the question is that can we absorb this 2 into K1 or K1 squared? So what was your name?
I'm Jai.
Jai, okay. Hi, okay, so anyone wants to maybe comment on that? That's a good question.
So she's asking whether we can absorb the 2 into the K1.
Yes.
Okay. Probably not, because because that okay, that is expectation of minus t square.
It's a very good question. I'll let you guys think about it and let me know. I think I can change that constant to something, let's say, bigger, or maybe smaller, at least bigger than 1, so by changing K1. But I'm not sure if I can, let's say, can we drop it like to 0.1? Is it doable? I'll let you guys decide, and maybe you can post on campus where. This is an interesting question.
I think if you set t equal to 0, then it doesn't matter what K1 is, and so you're going to get a 2.
Right. So yes, or at least going to be 1, because the probability has to be less than or equal to 1.
Yeah.
Right.
Yes.
So that most likely you can't drop it below 1 because you could have a random variable whose tail is like, the probability is like 0.5, right? But the question is that can I reduce it to anything smaller than like between 1 and 2 arbitrarily by changing k? Can I do that? Maybe. You think about it. It's a good question. Right? At least we know that we can get it the 2 from these results, right? So this type of bound that I showed here. You know that, for example, 1 implies, like we have shown, for example, this implication. So let's say this implies 1, we have shown. This is proposition 1, basically. Right, prop 1. But can we reduce this to any number in 1 and 2 by modifying A1 as well? I'll let you think about it. It's a good question. Okay. Other questions? So these are helpful. And in particular, for example, the moment one is interesting. So it says that the growth, so Gaussian variables they have a certain growth on the moments, and the moments are all bound. They're random variables who have finite moments for all of our order. But more than that, so there's certain growth. The moments can't grow too fast as you increase p. And also this characterization is very useful. So it's when you take it x to the power 2, it becomes much harder for it to have an MGF. I think of the Gaussian, for example, a Gaussian, this is going to be pi squared. The tails are going to be heavier. And so the fact that the MGF is bounded at some point is sometimes easier to verify. You just don't have to compute the entire moment-generating function. You just have to show that MGF is bounded for some, MGF of x squared is bounded for some lambda. And then when the expectation is 0, all of them are equivalent to this characterization that we've seen before. Okay. Questions about this slide? Questions, comments? Okay, so this characterization 4 can be used to define a certain norm. So we can define a Sub-Gaussian norm for a random variable denoted as this psi2 norm by the following sort of statement. The smallest p such that this MGF, like sort of MGF, so expectation of x squared divided with k squared is less than 2. So the smallest p that satisfies that is the Sub-Gaussian norm of x. And so a Sub-Gaussian variable is a variable whose Sub-Gaussian norm is fine. So x is Sub-Gaussian if and only if this is fine. So basically the smallest k4 in this property. Okay. So the smaller you make it, the harder this becomes because it becomes bigger. So x squared over t squared becomes bigger and the expectation would be infinite. And the fact that this is a norm, you have to verify for yourself. So it satisfies the properties of a norm. So it satisfies triangular inequality, homogeneity, and the faithfulness, they call it. Or you can just verify that for yourself. This is a valid norm on the space of Sub-Gaussian variables. So this you have to verify for yourself. And then using the Sub-Gaussian norm, all other constants that appear in these equivalent characterizations are within universal or numerical constants of that norm. So I can restate everything in terms of this. So there is some constant c, numerical or universal, such that I can write it in terms of this e to the negative c t squared divided by the Gaussian norm of x squared. Or I can say that the p norm of x is bounded by a constant times the Sub-Gaussian norm times root p, or this is by definition, this is just a definition of the norm. And in this case, again, there's going to be a c here, and Sub-Gaussian norm is squared. Okay, and you can also see that from this, that because this is going to also be like, you used to have e to the lambda squared sigma squared over 2, and this was sigma squared over, so you can see for the sigma squared, you have like explicit constants. But for the Sub-Gaussian norm, usually you don't keep track of constants. So you could write this is basically, you write something like this. This is in up to constants equal to this. So which means, I use this notation quite a lot. So this means that this is bounded by, let's say, C1C, also bounded below by C2 sigma. So or within constants of that. Okay. So there exist universal constants. C1 and C2, sometimes they call numerical constants. These are just numbers, they don't depend on anything else, such that C2 sigma and C1 sigma sort of sandwich that norm. For equivalent, you can say that sigma is between a constant, between two constants, or equivalently. So there exists, let's say, C3 and C4. Such that, and they're related to the other one. Okay, so the Sub-Gaussian parameter and the Sub-Gaussian norm are equivalent up to constant. Okay, I actually have it here, so you can see this is the Gaussian norm of x is sandwiched between, so that's the same as this. Questions? Okay, so there are a couple of interesting inequalities. So for example, it's easy to see the Sub-Gaussian norm is bounded by the L infinity norm. L infinity norm is just basically the essential supremum. So this is like essential. It's the supremum of the random variable, but we call it essential supremum of x. It's basically you want. This is, as a random variable is a function, it has a supremum. But the essential means we don't care about things that happens on measure, 0 sets. So a bounded variable has, so a bounded variable, a bounded infinity norm. It's going to be less than some, I don't know, b. Then this inequality says that the Sub-Gaussian norm of a bounded variable is bounded by constant times that b. And this you can, for example, verify from this result that we talked about, but we didn't prove. Sorry. Yeah. Sorry, this one. So this result here shows that the Sub-Gaussian parameter is controlled by the bound you have on x, and the Sub-Gaussian norm controls the Sub-Gaussian, sorry, the Sub-Gaussian. This guy controls the Sub-Gaussian norm, right? And so Sub-Gaussian norm is going to be bounded by the bound you have on the variable.
One question: what is this ESS soup?
That's the essential supremum, and I'll encourage you to read about this in Wikipedia.
Okay.
Uh,
Okay. Essential
right.
supremum. Okay.
Right, so the supremum or random variable is a little bit tricky to define because it's a random function. It's a function on the sampler space. And so if you modify the random variable on like a set of measure 0, the statistical properties are not going to change, right?
I see.
So you don't want to change the random variable at a single point, like put it on, like move it to a very large value, whereas everywhere else it's sort of much smaller. And so the essential supremum is not sensitive to perturbations on a set of measure 0.
I see.
Right. So but the way to define it is a little bit tricky.
I see.
If you're
Okay.
interested.
Okay.
Right. But essentially, if x is, so if x, let's say, is less than or equal to b, almost surely, this implies that this essential supremum is bounded by b.
Okay.
Right. And basically, it's the smallest b that satisfies this property. It's the smallest b such that the norm of x is less than or equal to b,
Okay.
almost surely. Something like that. Right.
Okay. Okay.
Okay, good question. Other questions? Okay, so this is one property. So this is one advantage of writing things in terms of norms. So you can see you can write down interesting inequalities, and I'm using here this notation. So this is saying that one side is less than or equal to a constant times the other side, and that constant is a universal constant. Okay, that just means what I wrote here. So this thing is, let's say this guy just means what does it mean? It means sorry. It just means this is less than or equal to c times x infinity. Okay, so now what do we do with this lemma? So this lemma is saying that if x is sub-Gaussian, then the centered version is also sub-Gaussian. But you know that's by definition. But the good news is that I can have a bound on the sub-Gaussian norm of the deviation based on the sub-Gaussian norm of the original x up to a constant. So let's give a simple proof of this. So the proof goes like this. So you write the expectation of x, the psi2 norm of this. So expectation of x is a constant, and a constant random variable is sub-Gaussian, because obviously, let's say. And the sub-Gaussian norm is just basically bounded. So this first statement is true. Why this first statement is true? Anyone?
Which statement?
This statement that I colored.
Oh,
I'm going to try to prove this.
okay.
Yes.
Okay.
I'm trying to prove the lemma 1.
Okay.
The expected value of x is constant and therefore bounded.
Yes. So what was your name?
Stephen.
Stephen. Okay. So yeah, so we can reuse this result. The sub-Gaussian norm is bounded by any bound on the variable. So the expectation is bounded by this. This is the bound on it. Right. So I can say basically that this guy is a bound on the expectation. Right. Expectation reviewed as a constant variable. This is basically its infinity norm. So the psi2 is up to a constant. This is bounded by the L infinity norm of that variable, which is just the absolute value expectation of x. And so this second inequality, why this is true?
I mean, inside things can cancel out, but the right hand side not, because you are taking
Right.
values.
Right. This is sometimes called triangle inequality, or you could do it by what other inequality, you know, that tells you this.
Jensen's inequality?
Yes, yes. Jensen's
Yes.
inequality does that.
Because of the
So,
no. Yeah, yeah, true.
right. So this is true. This one is definition of L1 norm. So remember the L1 or LP
Yes.
norm is this. The L1 norm is T equal 1. And I also know that, let's say with the L1 norm, I have not visible. For example, I know that X1 is less than or equal to, I can put it like a tool here, psi 2. So you know, remember that the K2 is bounded by a constant times psi 2 norm, and then root 1, right? Because P is 1. So the L1 norm is basically bounded by this, right? So I can do that. And that gives me this next. So this proves the result. So we have shown that, does it prove the result? We have shown that the psi 2 norm of the expectation of X is bounded by the psi 2 norm of X. Did I prove the result? Hello? Anyone?
That should prove the result if you just use the triangle inequality on the original thing, right?
Yes, so the idea is that this is a norm. So this is less than or equal to psi 2 plus expectation of this, since this guy is a norm. This is a triangle inequality.
Oh,
And so the first one is just good. This we're good with this. Right? This is what we want. And the other one, we also showed that it's up to a constant bounded by this, which is psi 2 norm of X. So the whole thing is bounded by a constant times the psi 2 norm of X. So to prove this result, this helps you control the centered and the sub-Gaussian norms of the centered variables in terms of the sub-Gaussian norms of the original variable. But I should warn you that in practice, this guy could be much smaller than the other side. The inequality is true, but sometimes one side is much smaller than the other side. Anyone can, for example, give an example of something like this from the things that we have seen before. So if I have a random variable x, the claim is that the psi 2 norm or the sub-Gaussian norm of the x minus expectation of x could be much smaller than the sub-Gaussian norm of x. I'll give you a few seconds to think about.
Maybe like a non-zero constant random variable.
yeah, whose expectation is bigger than 0.
Okay, that's good. That was easy. Okay. Yes, non-zero constant variable, then one side is 0, the other side is non-zero. Good, but can we like get another? Somehow you have to read my mind, what I'm thinking. So let's look at this, for example. Something which is genuinely random. So let's look at this slide. Does this give you any ideas? This one. So if I look at Sn, the sub-Gaussian normal is generally going to be like root n. You can see from this, but Sn minus the expectation of Sn. Sorry, so what I was saying is not but this this guy versus this guy, the order of things would be different. So this one would be of the order root n. This one is probably going to be of the order n. Okay, so this you verify for yourself, but that's the case of the things where when things are dependent on n, sometimes just think generally this holds. So this is of the order root n, this is the order n. If it's wrong, then let me know. But that's what would happen. So at least the root n case you can see from here. So this is of the order, let's say if sigmas are all equal. So sigma I is equal to sigma. So then, sorry, let's say sigma 0. Then this is sigma is going to be root n times sigma 0. It's going to scale like this, but generally this guy Sn is just the sum of a bunch of things. And if you don't center them around 0, then when you add them up, it's just going to scale like n. Okay, this is the example, but let me know if it was wrong. Okay, questions? You're almost out of time, but let me just mention one last thing. So this the same slide. Go off. This same slide can be written in terms of the Sub-Gaussian norm. So if we can restate this as Sub-Gaussian norm of Sn. So here is 0 mean. So this is I shouldn't have put this here. So generally, if let's say if Sn is non-zero, and this is the case where xi have non-zero mean. If they're 0, then it's fine. They're the same basically. So here Sn has 0 mean in the original case. So the psi 2 is up to a constant equal to sigma, which is equal to root. So let's say this. This squared is equal to this squared, which is equal to sigma I squared. And this is up to constant equal to sum I from 1 to n. Xi psi 2. Right, so the Sub-Gaussian norm is squared. So the Sub-Gaussian norm, we can say that the Sub-Gaussian norm again, Sub-Gaussian norm of the sum I from 1 to n squared is up to constant sum I from 1 to n xi. So this is not exact inequality, but up to constants. Right, so you can see this twiggly thing. But this is a restatement of this result in terms of the psi 2 norm. Because everything holds up to a constant, you can replace the Sub-Gaussian parameter with the Sub-Gaussian norm. Okay, and this gives you this other result. So you're out of time, but this is going to give you this result. And this is, for example, how the HDP work states this type of thing. The high dimensional statistics works with the Sub-Gaussian parameter, and the high dimensional probability works with the Sub-Gaussian norm. And they're almost equivalent, and each one has its benefits and drawbacks. So we're going to work with both, basically. Okay, any questions? We should stop here. Questions, comments? No questions. Okay, so I'm going to maybe wrap this up then. Stop. Okay, so I'm going to hopefully post a homework problem in the next couple of days. either tomorrow or tonight, maybe, or tomorrow, or in Friday. And it would be usually due 2 weeks from now. And then hopefully we'll come back and continue next week. Okay? Questions? Comments? Okay, so see you next time. Bye-bye.
Bye.
Bye.
Thank you.
Thank you.
Bye-bye. Thank you. No problem.